So welcome back, ladies and gentlemen, to another exciting chemistry video. Today we are going to be wrapping up unit number 3 by focusing on the concepts of spectroscopy and the photoelectric effect. So what we're primarily going to be looking at is how does light interact with matter on an atomic level. So we're going to be looking at transmissions of light, we're going to be looking at patterns of absorption and reflection, and understand how we can utilize those concepts in a lab-based setting. So let's get started. So hopefully by the end of this video, you'll be able to explain different types of radiation and their relationship with motion or electronic transition, relate the amount of energy increase or decrease to the energy absorbed or released by a photon, use formulas to solve for energy and wavelength, explain how spectroscopy can measure concentration based on the absorption of light, and evaluate possible sources of error that would result in an increased or decreased concentration based on the absorption of light. So we've got a lot we need to cover today. Let's go ahead and get started. So let's talk a little bit about the electromagnetic spectrum. Now, you've probably talked a lot about this in other science classes. It is basically the full radiation of wavelengths going all the way from gamma radiation to radio waves. You'll notice that the wavelength in meters is the smallest all the way to the left side when we look at gamma radiation, very dangerous radiation, and largest when we look at things like radio waves. But if you look right there in the middle, there's a very, very small little window where we have a visible light spectrum, and this typically ranges in wavelength from 400 to 700 nanometers. These are the different colors that you see. Now, using different types of radiation actually tells us important information about molecules. Certain wavelengths of light cause electrons to jump from a ground state to an excited state. So think about when we've talked about the electron configurations. What causes an electron configuration to be in an excited state? And typically, an electron has absorbed a specific wavelength of light that allows it to jump from one energy level to the next. Now, when it goes from the excited state back to the ground state, it emits a photon of a specific color and wavelength. We need to understand that the amount of energy that is absorbed is very specific. It is very finite. It is not a continuum like a lot of things that we've discussed in chemistry. It is a very specific amount of energy that is absorbed that results in the emission of that light. Furthermore, different elements are going to absorb different amounts of energy, and therefore when they go from the excited state back into the ground state, they are going to emit different wavelengths of light. We can see this in a variety of different elements. So again, different types of radiation result in different types of motion or electronic transition, and this actually helps us identify types of molecules, bonds that are present, those types of things. So the key thing here is to just simply know these 3 different types of motion or electronic transitions based on the different types of electromagnetic radiation that cause them. Microwave causes rotational. I always remember that because I think of the little rotating thing in the microwave that rotates your food. Easy enough. Infrared tells us about vibrational transitions, but the key one we're primarily going to be looking at is UV-Vis, which is electronic energy. That is what we talked about previously about the photons that are emitted in different colors of light. So one thing that is very useful about these concepts, and again, this is directly correlated to what you see here known as the photoelectric effect, where the emissions of electrons when electromagnetic radiation hits something. Again, these are specific wavelengths of electromagnetic radiation that cause these jumps or removal of these photons. Now, calculations can be made based on the wavelength, frequency, and the speed of light. We can utilize these variables in order to calculate the amount of energy, the wavelength, frequency, etc. So here we have an equation where C equals lambda nu, where C is 3.00 times 10 to the 8th meter per second. Lambda is your wavelength, and nu is your frequency. So we can just simply take one of those variables, plug it in, and be able to solve for that. Now, we can also determine the energy of a photon that is removed due to the photoelectric effect by using this other formula, where E equals Planck's constant times nu, where Planck's constant is 6.626 times 10 to the negative 34th. So we can kind of combine these equations together and substitute them out and get E equals hc over lambda, where h, again, is Planck's constant, c is the speed of light, and we can directly correlate the wavelength in meters to the amount of energy of a single photon in joules. So let's do a sample problem and see what that looks like. So let's determine the energy of a photon emitted by a substance that is hit with light that is 421 nanometers. So again, we're going to be utilizing these formulas and the constant values that are listed. So we can combine these together. I'm going to take it one step at a time in order to be able to calculate that. The energy is what we're going to be solving for last, so what we need to do is to be able to calculate the frequency. So what I'm going to do is I'm going to take the very first equation. We're going to use 3.00 times 10 to the 8th meters per second, which is the value for C. I am then going to add in the wavelength in meters as opposed to nanometers. So you're going to need to be able to go through and calculate that. Or you should just know that if you have something that is in the UV vis spectrum, which is in nanometers, basically make it a number between 1 and 10 and smack times 10 to the negative 7th on the end of it, and you've converted nanometers to meters. Or you can remember that 1 nanometer is 1 times 10 to the negative 9th meters. So I'm going to go through and I'm going to solve for nu, which is going to give me my frequency. Frequency is measured in hertz, so we have 7.12 times 10 to the 14th hertz. I'm now going to plug that into my E equals h times nu equation and utilize Planck's constant, which is 6.626 times 10 to the negative 34th times nu, and that's going to give me my energy in joules, which is 4.72 times 10 to the negative 19th. One way to go through multiple choice questions relatively quickly is that if it is in between 360 and 720 nanometers, which is essentially your visible light spectrum, that your energy is always going to be something times 10 to the negative 19th. So it's pretty easy to look at some multiple choice questions to be able to solve those relatively easily if we have that bit of information. So let's talk a little bit about the Beer-Lambert Law. It is possible to utilize the ratio of the absorption of light to determine concentrations of solutions. Think about it. Solutions that are more concentrated absorb more light than those that have a lower concentration. So this is explained by the Beer-Lambert Law, which is given below. Now you don't need to calculate that, but there are a couple things that I want you to be able to understand. What I want you to do here is I really want you to notice on the right-hand side here, because what we're looking at is chlorophyll. Notice the color of light that is absorbed by all of this compared to the color of light that is reflected. So you see the amount of light absorbed by the chlorophyll that is present inside of a variety of different plants. And notice where the absorption is the lowest. It's in that green range, right? If you look at the bottom, kind of between 500 and 600 though, your greens and yellows are your least absorbed colors of light. And that makes sense if we think about plants, because when we see them, we see green. And that light is the light that is being reflected. We don't see very many blues or reds. Typically, when we do see red colors, it's because chlorophyll A and chlorophyll B, the amount that is produced by plants decreases as we get closer to the fall. And so as a result, you start to see more of those oranges and reds and really pretty fall colors that we talk about. But utilizing the Beer-Lambert Law, we can use the ratio of absorption of light to determine concentrations of solutions. And we do that using a spectrophotometer. These are used to measure absorptivity. The first thing we need to do is alter the wavelength to find the maximum amount of absorbance. That is going to be very key as we go through and run different samples. So as you look at the apparatus there on the right, you have a little device there that allows you to alter the wavelength that is being shot through the device. And what you do is you take a little cuvette, which looks like a very, very small, fragile test tube, and you insert it into the machine on the very left-hand side here. It's basically just like a little place for you to insert the cuvette, and then you can take readings of absorption and graph those out based on the concentration of the solutions, when what you'll get is a linear relationship. As the concentration of the solution increases, the absorbance increases as well. And so we can make a best fit line, and then we can measure unknown concentrations of solutions. So it's a very, very useful tool. A couple things to be aware of this. You are going to want to use a blank each time. So before you insert whatever you're trying to measure, you're going to take a cuvette, you're going to wipe it clean, and then you're going to fill it with water, and then you're going to insert it into the device and zero out the machine. Okay, very similar to kind of how you zero out a scale before you mass any particular substance. Now, error is quite common in the use of spectrophotometers. Incomplete wiping of cuvettes which have smudges would increase the absorbance, thus having an assumed higher concentration. Remember, it's measuring the amount of light that goes through the cuvette. You have a device over here that detects how much light is going through. Your cuvette is here. If there are fingerprints on it, then less light's going to reach the detector here, which means that your absorbance reading is going to be higher than what you would anticipate. Furthermore, not drying cuvettes can leave water behind, and when we have excess water that's left in a cuvette, that can dilute a solution, thus resulting in a lower concentration. So we want to be very, very careful when we go through and work with these devices, as a variety of sources of error are possible when using spectrophotometers. However, the tool itself is quite useful when looking at the direct correlation between the concentration of a substance and the absorbance. So again, today's focus was primarily on electronic transitions and on how we can use light to look at a variety of different properties on a molecular level. And hopefully you can calculate the amount of energy or wavelength of an electronic transmission. Also, you should be able to understand and explain the concepts of spectroscopy and possible sources for error. This is the end of Unit 3. We're making great progress. I hope you've enjoyed the video. Make sure you like, comment, and subscribe. And as always, if you have any questions, make sure that you reach out and let me know. Have a great day, and we will see you soon. Bye.